This is the third lecture out of chapter 22, so this will be the last lecture. So we'll cover a couple of main concepts and reactions in this lecture, what's known as the Michael addition and the Robertson annulation. Okay, so if we have a molecule like this, so this is an alpha, beta, and saturated ketone. And so what's important to recognize here, so these can undergo what's known as 1,2 or 1,4 addition. So if we take this alpha, beta, and saturated ketone and number it, so 1, 2, 3, 4. So it's not a nomenclature, it's just numbering things with respect to each other. So we're numbering through that conjugated double bonds. So what's important to recognize is that so this carbon has partial positive charge density, right? And that's easy to illustrate if we just draw some resonance structures for this molecule. So we can take those two electrons and move them there. So oxygen's negative, and that carbon can bear a full positive charge, or since it's attached to oxygen, it's got some positive charge density to it. So alpha, beta, but what's important to recognize is that the beta carbon also does. So if we draw another resonance structure, so we can move these two electrons there, and we can put a full positive on that beta position. So the full positive can be on the carbon number 2 or the carbon number 4. So if we react an alpha, beta, and saturated aldehyde or ketone with a nucleophile, the nucleophile would tend to react at carbon number 2 or carbon number 4, the beta carbon, because that's where the positive charge density in the molecule is at. So strong nucleophiles tend to react at carbon number 2, so they tend to react at the carbon-oxygen double bond. And weak nucleophiles tend to react at the beta carbon, carbon number 4. And so when we say weak, it's not weak like in the sense of SN1 and SN2 nucleophiles, weak relatively speaking. So like lithium aluminum hydride, Grignard reagents, and organolithium reagents are very, very strong nucleophiles. And so they tend to do 1,2 additions. So LaH, source of H minus, right? So this would just go here, and this would become an O minus, which would then pick up a hydrogen in the second step. Right, so that would be your product. So in this case, the H minus is the nucleophile. It did 1,2 addition, so 1, 2. So the nucleophile went to carbon 2. Or if you have a Grignard reagent, Grignard reagents are very strong nucleophiles. They tend to react here as well. So take whatever's attached to magnesium, attach it to that carbon number 2, and the C double bond O becomes an O minus, which picks up a proton in the second step. Oops, sorry, the C double bond C should still be there. Right, so you would make that product. Or if you had an organolithium reagent, they're also very strong nucleophiles, so that would also attack at carbon number 2. Right, so nothing happens to the C double bond C. It's the C double bond O that reacts in these cases. But if you use a more mild nucleophile, then they tend to do 1,4 additions instead, since that carbon does have some positive charge density on it. So if you reacted it with a cuprate instead of a Grignard reagent, so cuprates are much less reactive, so then this carbon attacks here, and those electrons go there to make a lone pair. So now nothing happens to the C double bond O. It's the C double bond C that reacts instead. And then that carbon with the lone pair would pick up a proton in the workup step. Right, so that would be your product. So that would be what's called a 1,4 addition. So with respect to the oxygen, 1, 2, 3, 4. So you reacted at the 4th position or the beta position. So predicting these products is easy. So take whatever the nucleophile is, stick it on the beta carbon, and basically erase the carbon-carbon double bond, and you've got the product, right? So CN minus, cyanide relative to Grignard reagent, or an organolithium reagent is a weak nucleophile, so they would tend to do 1,4 addition as well. So again, initially you would have a negative there, and then that would pick up a proton from the solvent. So again, you stick the nucleophile on the beta position, erase the carbon-carbon double bond, and that's your product. Or RS minus would do 1,4 additions as well. And whatever's attached to sulfur is just along for the ride. Okay, so annulates react at the do 1,4 additions as well. And so when an annulate does a 1,4 addition, that's what's called a Michael addition. Okay, so if we took a molecule like this and reacted it with a base, so you can deprotonate that carbon, and so now you have an annulate, and the annulate would react at the beta carbon. So that's the Michael addition. Okay, so now we would have so this is malonic ester that I'm using, right? If you remember that from a previous lecture, first lecture in this chapter. So the annulate of malonic ester would do a 1,4 addition, and then that's going to pick up a proton from the solvent. Okay, so now you have that, and if that's all you did, you could conceivably stop at that point, but if you want another step, and if you did H2OH+, then that's going to hydrolyze the two esters, right, to carboxylic acids. Okay, so now these are carboxylic acids. And now if you heated that up, so you don't have to heat it, you could conceivably try to stop at that point. But if you did heat this up, then that can lose CO2. But it can only lose one of them, right? Because once you lose one, so alpha beta, then the other C double bond O would no longer be next to us. The other carboxylic acid would no longer be next to a C double bond O, so it could not decarboxylate. So you could just decarboxylate one of these. Okay, so that CO2 is gone, and bump hydrogen down into its place, and that would be your final product. Right, but the point is, so this first two steps is the Michael addition part, where an annulate reacts at an alpha beta unsaturated ketone. Okay, so this is kind of the culmination of all of this. So doing a reaction like this is what's known as the Robinson annulation. Robinson annulation is one of the most complex reactions discussed in Organic 1 and Organic 2. So obviously it looks complex, right? If you start with this and you end up with that, that's the final product. So what's going on in this reaction? So Robinson annulation is a sequence of reactions. First of all, it's a Michael addition. And then once you do the Michael addition, then you follow that by an intramolecular aldol condensation. That's the sequence is what's called a Robinson annulation. Okay, so how does this work? So if you took these two molecules and reacted with a base, then you're going to make an annulate. So where can you make an annulate at? So you can make an annulate here, and those two are equivalent, right? So we'll call those A. Or you can make an annulate there, B. Or you can make an annulate here, C. Not here, because that's a sp2 hybridized carbon. Okay, so where's your most acidic position? Well, it's going to be B, right, between the two carbon-oxygen double bonds. That way the annulate that you make would be resonance stabilized by both C double bond O's. Okay, so if we step through the mechanism, how this reaction works. So first of all, you make the annulate, and then annulates do Michael additions. So now you're going to take that and react it at this position, and then those electrons go there. Okay, so now what we're going to do is we're going to pick up a proton on this carbon to give that. So that would be your Michael product. All right, you made an enolate. The enolate did a 1,4 addition. That's the Michael addition. And then the enolate that resulted from that picked up a proton from water to make the Michael addition product. Okay, but it doesn't stop at this point because you just made hydroxide again. So it's still setting in base, which means you can make enolates again. So how many places can you make an enolate? So you can make an enolate there, 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 and you can make an enolate there. So A is equivalent B, C, and D. Okay, so obviously you can see where I made it at is I made it at D. Why did I make it at D? Well, so if you make it at B, what could you do then? If you made an enolate here, then it could only react there, and that would be a 1, 2, 4-membered ring. 4-membered rings are difficult to make. If you made it at C, where could C react? So if you made an enolate here, then it could react here, and that would be a 1, 2, 3, 4-membered ring as well, and that's not favorable. If you made it at A, where could A react? Well, A could react here. That would be a 1, 2, 3, 4, 5, 6-membered ring. 6-membered rings are easy to make, but this one would not be because you would have to go over the top of that cyclohexane ring in order to make the new ring. So that's not favorable. Whereas if you make it at D, then if that reacts here, so that's a 1, 2, 3, 4, 5, 6-membered ring, and again, making 6-membered rings are favorable. So you can make the enolate at A, B, C, or D. So hydroxide could take a proton off, but then that can go backwards, and it can put the and water can put the proton back on. So once you take the proton off at D, though, then that's set up to do an intramolecular aldol reaction, which is favorable because making 6-membered rings are favorable. So as soon as you make the enolate at D, then that reacts with carbon number 6 and kind of gets trapped. Okay, so we're going to make a 6-membered ring. So we already have a 6-membered ring here. So we said this is carbon 5 and 6, and so we're going to have another 6-membered ring fused to carbon 5 and 6. So let's draw another 6-membered ring fused to 5 and 6. So 5 is attached to 4, 3, 2, and 1. So 4 has a methyl, 3 is a CH2, 2 has a C11O, 1's a CH2, and 6 has the O minus, right? Because the C double bond O became a CO single bond. So that's the intramolecular aldol. Now if we pick up, well, hydrogen on that oxygen, which you wish you could do that on a test if you're drawing mechanisms, just copy and paste so you don't have to draw these things again. Okay, so that will be your aldol product. And so if you were not heating, then you could potentially stop at that point, but if you're heating, and we're heating in this case, so then we're going to do a dehydration step now. Okay, so let's sketch out these hydrogens because we're going to use one of them. So we're going to take lone pair of electrons and make a bond to one of those two hydrogens. Those electrons go there and kick off OH minus. And now you have that, right? So now you have an alpha beta unsaturated ketone, so that would be the dehydration product. Okay, so that sequence of reaction is what's called the Robinson annulation. So a fairly complex reaction, right? Given the starting materials, not easy to see what the product is. So that's, again, what makes this chapter harder than other chapters. You have to be able to think about the steps in between in order to get to the final product. So you have to really know how this reaction works in order to sketch the final product out. All right, and there's a lot of steps in between. Okay, so that's pretty much the material in this chapter. So lastly, in this lecture, let's just take a few examples from, there's one more reaction, this Amine Alkylation, and then we'll finish just by working three problems out using some of the stuff that we've talked about in this chapter so far. Okay, so last new reaction, an Amine Alkylation. So this is from previous chapter, right? If you take a ketone or an aldehyde and a secondary amine, NH+, then that's the recipe to make an enamine. So if you remember how to predict the product there, this nitrogen gets attached to there, you lose water, right? Oxygen goes away ultimately as water, and you make a double bond on one of the two sides of the C double bond O. So you would make this, which is an enamine. So the significance of this is that, we can draw a resonance structure of this, or you can have a negative charge on that carbon. So negative charge there, which ultimately that's the alpha position to a C double bond O. So you can use this to do an alkylation. So now if you react this with an alkyl halide, so if we do this sequence of reaction, first make the enamine, and then do an alkylation, and then do a hydrolysis. So those electrons can go here, kick off the bromine, and now you have a carbon-nitrogen double bond. It's like an imine, but it's positively charged, so it's an aminium ion, and those can be hydrolyzed back to the C double bond O. So if you take this and react this with water, basically this goes away, and you replace that with the C double bond O. So you get your ketone back, and you've alkylated it with whatever the alkylating group was in the second step. You've done an alpha alkylation. Okay, so that's it for the reactions in this chapter. And so lastly, let's just work three more problems using some of these reactions that we've covered. Okay, so if we do this, so we have a ketone, we have an ester, and we have a base, which means we can make an enolate. So there, or there, right? All of the positions adjacent to the C double bond O. Okay, so where's it going to go? A, B, or C? Well, so A and B are alpha to a ketone, and in the last lecture we said that those positions are more acidic than alpha to an ester, so we can forget about C. We're not going to make the enolate there. So we're going to make it at A or B. Well, if you make it at B, what can it do? So if you make an enolate here, it could react there, but that would be a 4-membered ring, and that's not favorable. If you make it at A, then it could react here, and that would be a 6-membered ring, and that's favorable. So that's what's going to happen. So you're going to make the enolate at A. And then that is going to react here and break the double bond. So now you're making a ring, so let's number. So 1, 2, 3, 4, 5, and 6. Okay, 1, 2, 3, 4, 5, and 6. So 1 is a CH2, 2 is a C double bond O, 3 is a CH2, 4 has benzene attached, 5 is a CH2, 6 has the O minus, and the OET attached. And then, so this is a common mistake students make all the time, is now they put an H plus there and call it done. But you don't make an OH at this point, right? If it's an ester, you remake the C double bond O and you kick off that. So you make that, you make the beta diketone. So that would be your major organic product. Okay, and this one, so LDA is a strong base, so that means you're going to make an analyte, right? Both sides are equivalent, so it doesn't matter where. So LDA will take off a proton and make an analyte here. And then that carbon's negative, that one's positive, so they're going to react with each other, so that goes there, that goes there. Okay, and then, so that's what you get after the second step. So after the, now you do the next step. So we're going to pick up a hydrogen from water to make the OH. And then this is going to dehydrate. So with the base, so there's a hydrogen there. So we're going to take a lone pair, take this hydrogen off, right? Because that's an aldol product at this point. And then OH leaves. So you make that, which is a highly conjugated double bond, right? It's conjugated both with benzene and it's conjugated with the C double bond O. So that would be the product from that sequence of reactions. Okay, so lastly, let's work one more Robinson annulation. Okay, so we have an alpha beta unsaturated ketone, so that's going to do the Michael addition. So how many places can you make an analyte? So we can make one there. So we have a base. Aldehydes and ketones and esters, we're going to make an analyte, or you can make one there. So we'll call this A, B, and C. So which is the most acidic? Is going to be A, right? So B, so this is not a great place, not as good of a place to stick a negative, because this C double bond O is already tied up in resonance with the alkene. So putting the negative on C is not the best place. Putting the negative on A is the best place. So what you would do is you would lose a hydrogen from here. So the OET minus would take one of those hydrogens off and put the negative on that carbon alpha to that C double bond O. So that would be the preferred analyte. So that's the most acidic position because that negative charge is resonance stabilized through the C double bond O and the benzene ring. So that makes those hydrogens the most acidic. Okay, so that's your analyte. So you make an analyte. So what analytes do, they do Michael additions, so 1,4 additions. So this then is going to attack here, and that becomes a lone pair. Okay, so lone pair there now. That's C double bond O. So now you have that. And have I lost anything? Yes, I lost the OCH3 group. It's still there. Okay, so that's what we have so far. So now we pick a proton up on that carbon from the solvent. And then we want to reform an analyte. Now we want to take a proton back off. So we put one on, now we're going to take one back off. Because so that analyte, so again, so we could make several different places we can make analytes. here, 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 and here, but only one leads to forming a ring that's stable, right? Because if you make it A, and if it reacted at this carbon, you would have to react across the cyclohexane ring. If we reacted at B, then if it reacted at this carbon, you would have to make a 4-membered ring. If you make it at C and it reacted at this carbon-oxygen double bond, that would be a 4-membered ring. That's not favorable. If you reacted at D and then that reacts here, then that would form a 6-membered ring. And we lost a methyl group, didn't we? Yes, there should be a methyl group here. And there should be a methyl group there. So we're going to make it at D, and then D is going to react at the C double bond O on top to make a 6-membered ring. So we're going to make an annulate at D. So we're going to take a hydrogen off. So we use another OET minus. Take a hydrogen off. Put the lone pair there. Let's clean this up a little bit. Okay, so we took a hydrogen off of there, so now the annulate is there. Now this is going to close here into a 6-membered ring, so that's an intramolecular aldol. So let's number. So 1, 2, 3, 4, 5, and 6. Copy and paste. Okay, so we're going to have a 6-membered ring fused to 5 and 6. Okay, so let's see. So 4, 3, 2, 1. So 4 and 3 are CH2s. 2 is a C double bond O. 1 has a methyl group on it. 6 has the O minus on it. Okay, so almost there. And now we pick up a hydrogen on the oxygen from the solvent. And then lastly, we want to do the dehydration step. So there's a hydrogen here, right? That hydroxide, or the conjugate base of ethanol. I think that's the base we were using. So that takes this hydrogen, those electrons go there, and that comes off. So now the double bond is between carbon 1 and 6, right? So that would be your final product. So that would be the aldol condensation product. Oops. Okay, so it's a pretty complex reaction. So hopefully that made sense and you can work through one of those on your own. All right, so we will stop there.